My name is Matthew Cowell, and I will be sharing our CVPR 2024 highlight paper, Understanding Video Transformers via Universal Concept Discovery. Interpretability methods like network dissection have greatly increased our understanding of how image-based models function. For example, early layer neurons activate for low-level concepts like color and textures, while mid and late layer neurons capture concepts like objects and their parts. Alternatively, video transformers have been shown to be very effective at different video-based tasks such as action recognition and video object segmentation, but there's a limited understanding of what concepts are captured by these models in their intermediate representations. And that brings us to the main problem. There's no existing concept discovery methodology for deep video models. Our solution is VTCD, Video Transformer Concept Discovery. Let's explain the method of VTCD. The method consists of two main components, concept discovery and concept importance. Let's consider the task of semi-supervised video object segmentation, where we take a set of videos with a query frame, pass them through our video transformer to produce output segmentation mass. We then obtain intermediate representation Z and perform slick clustering on this representation to produce tubelets. We repeat this clustering for several videos to produce a dataset of tubelets. We then cluster these tubelets across the dataset, and the output of this clustering are the discovered concepts. Let's now quantify how important these concepts are to the model output. We do this concept discovery for all heads and all layers of the model, and then perform Monte Carlo sampling that randomly masks out different concepts in each head while computing the drop in model performance. A concept's importance is the average drop in performance over all masks. Let's look at some results. We first visualize the most important concept for different models, starting with the TCOW segmentation model trained to track occluded objects. The most important concept, at layer 5, captures target object as well as objects with similar appearance, suggesting the model solves the disambiguation problem by first identifying possible distractors in mid-layers. The second most important concept, at the 9th layer, tracks the target object throughout the video. We also examine the most important concepts for the supervised video AMAE model trained on SSV2 for action recognition, targeting the class, dropping something into something. The most important concept at layer 11 captures the object being dropped until the dropping occurs, at which point both the object and the container are highlighted. The second most important concept appears in layer 8 and captures the container without highlighting the object. Observing the third most important concept reveals similarities across model representations. Both models are found to have temporally invariant concepts, suggesting positional information processing occurs in early layers of the model. This raises the question, what concepts are universal across all models trained for different tasks? Inspired by the Rosetta Neurons paper that looked for universal neurons in image models, we proposed the idea of Rosetta concepts. We analyze 4 different models, a segmentation, action recognition, self-supervised, and video language model. We identify Rosetta concepts by looking at the IOU of the tubelets for each concept. If the IOU is above a certain threshold, delta, we consider the concept universal across the 4 models. We also look at subset of the models such as 3-tuple Rosetta concepts and 2 tuples. Shown is an example of a Rosetta concept shared by all 4 models capturing rolling objects with an IOU of 18%. We find many other interesting concepts throughout the model. At early layer, we see spatially and temporally invariant position concepts. In mid layers, we find object-centric concepts such as rolling objects and hands. At deeper layers, we find spatio-temporal object-centric concepts, capturing objects or containers before dropping events. Notably, these models are not trained with any ground truth concept information, and these concepts are fully emergent. We apply VTCD for 2 applications. First, we find and use object tracking concepts in any pre-trained model to perform zero-shot semi-supervised video object segmentation. Second, we can use our concept importance metric for model pruning. We target the most important transformer heads for the 6 spill classes in SSV2. Removing the least important heads actually improves performance while reducing the flops by up to 50%. Please visit our project page and paper for code and more results, and we hope to see you at our poster at CVPR this year.